An extraordinary sequence of seismic events in northern South America has transformed part of the southwestern coastline of Trinidad into a striking example of the immense forces constantly reshaping the Earth. Within the span of a single day, two major earthquakes struck inland Venezuela, sending seismic waves across the Caribbean and leaving behind evidence that extended far beyond cracked roads and shaking buildings. Along the Galfa Point area near Cedros, residents encountered a shoreline that no longer matched the one they had known only hours earlier. Large sections of previously submerged seabed had emerged into daylight. Marine animals lay stranded across freshly exposed sediments, and fractures split the landscape in unexpected directions. Every observation pointed toward a coastline that had experienced rapid vertical movement rather than gradual change. Several important questions immediately emerged. Why would an earthquake occurring inland Venezuela alter the coastline of Trinidad? What geological process is capable of raising part of a shoreline by an estimated 20 feet, or approximately 6.1 meters, in such a short period? Does this remarkable transformation represent an isolated event, or does it reveal deeper tectonic processes that have been active beneath the Caribbean for thousands of years? These questions have driven close examination of one of the most unusual geological developments reported in the region in recent decades. The seismic sequence began on the 24th of June, 2026, when a magnitude 7.2 earthquake struck northern Venezuela. Before regional stresses had fully dissipated, a second and even stronger magnitude 7.5 earthquake followed within the same tectonic setting. Rather than representing two unrelated earthquakes, the pair formed what seismologists commonly describe as a seismic doublet, a relatively uncommon occurrence in which two very large earthquakes happen close together in both time and location. Such seismic doublets can produce far more complex ground deformation than a single earthquake. Instead of releasing accumulated tectonic stress through one principal rupture, the crust adjusts through multiple fault movements that redistribute forces across a much broader area. This redistribution can affect regions located considerable distances from the primary fault rupture, particularly where geological conditions favor secondary deformation. Trinidad occupies one of the most geologically complicated locations in the Caribbean. Although often associated politically and culturally with the Caribbean islands, Trinidad lies immediately adjacent to the northern coast of Venezuela. The island sits within a transition zone where the Caribbean plate interacts continuously with the South American plate. These enormous sections of the Earth's lithosphere have been moving relative to one another for millions of years, generating networks of active faults, folded sedimentary basins, mud volcanoes, hydrocarbon reservoirs, and recurring earthquakes. Unlike the clearly defined boundaries seen in some tectonic settings, the interaction between these plates is distributed across numerous faults and deforming sedimentary layers. Energy released during one major earthquake may therefore influence geological structures extending well beyond the principal rupture zone. Initial reports following the earthquakes focused largely on shaking experienced throughout Trinidad and neighboring regions. Residents described prolonged ground motion, while authorities evaluated infrastructure for potential damage. Yet as attention gradually shifted toward the southwestern coastline near Cedros, observations emerged that suggested something considerably more unusual had occurred. Individuals visiting Galfa Point encountered stretches of newly exposed coastal terrain where seawater had previously covered the surface. Marine organisms including fish, crabs, clams, and stingrays were found stranded across the exposed seabed. Their presence provided immediate evidence that areas formerly lying beneath tidal waters had become permanently elevated above sea level. Unlike the temporary retreat of water associated with tides or tsunami drawdown, this newly exposed terrain remained visible. The shoreline itself appeared to have shifted seaward as portions of the seabed emerged above the waterline. Additional observations reinforced the impression that significant geological deformation had occurred. Fresh fractures extended across sections of the coastline. Small landslides affected unstable slopes near the uplifted area. Pools containing bubbling water attracted attention because they indicated movement of fluids through newly opened pathways within the underlying sediments. Natural oil seepage was also reported, suggesting that subsurface pressures had altered enough to allow hydrocarbons to migrate toward the surface. Taken individually, each of these observations might have reflected localized instability. Together, however, they painted a consistent picture of extensive crustal deformation affecting the coastal environment immediately following the seismic doublet. One of the earliest geological assessments came from geologist Xavier Moonen, who visited the affected coastline to examine the changes firsthand. His observation suggested that the uplift was associated with what is known as a toe thrust, or reactivated slump mechanism. This interpretation differs significantly from the common assumption that all earthquake-related uplift results directly from movement along a major fault reaching the surface. In sediment-rich coastal environments, particularly those containing thick accumulations of water-saturated sediments, powerful earthquakes can destabilize entire packages of material resting on gently inclined slopes. When these sediment masses begin moving downslope under gravity, compressional forces build at their leading edge. Rather than allowing all material to continue sliding freely, resistance develops near the front of the moving mass. The resulting compression forces sediments upward, producing localized uplift where the leading edge effectively buckles. Geologists refer to this process as a toe thrust because deformation occurs near the front, or toe, of the moving sediment package. If an older submarine slump already exists beneath the coastline, powerful earthquake shaking can reactivate that ancient instability, producing renewed movement along previously weakened surfaces. This explanation aligns with the observed pattern at Galfa Point. Rather than requiring the entire coastline to rise uniformly, localized sediment compression could elevate specific sections substantially, while neighboring areas experience much smaller changes. Southwestern Trinidad possesses geological conditions capable of supporting such a mechanism. Over countless thousands of years, rivers flowing from both Trinidad and Venezuela have transported enormous quantities of sediment into nearby marine basins. Layer upon layer of sand, clay, silt, and organic material accumulated beneath shallow coastal waters, forming thick deposits that remain saturated by groundwater and seawater. These sediments do not behave like solid bedrock. Instead, under sufficient stress, they may deform plastically, shift along buried slip surfaces, or experience liquefaction in certain conditions. Large earthquakes dramatically increase the likelihood of such movement, because intense shaking temporarily reduces the strength of saturated sediment layers. Once movement begins, deformation may continue until a new state of mechanical equilibrium is established. In some cases, compression produces localized uplift instead of simple horizontal displacement. Reports indicating an uplift approaching 20 feet, approximately 6.1 meters, attracted immediate attention because such vertical movement would represent an exceptionally significant coastal change. Local geologists have indicated that portions of the Galfa coastline may have experienced uplift reaching that magnitude following the Venezuela seismic doublet. At the same time, geological reporting has remained appropriately cautious regarding this preliminary estimate. Although field observations strongly support the conclusion that substantial uplift occurred, the full magnitude of vertical displacement has not yet been independently confirmed by national or international geological agencies through comprehensive surveying techniques such as satellite interferometry, differential global positioning system measurements, or detailed topographic mapping. This distinction remains important because rapid field estimates often evolve as additional measurements become available. Initial visual impressions can sometimes underestimate or overestimate actual displacement, depending upon local topography, tidal conditions, erosion, and pre-existing shoreline geometry. Nevertheless, even if future surveys ultimately refine the estimated amount of uplift, the observed emergence of previously submerged seabed represents compelling physical evidence that measurable vertical deformation unquestionably occurred. The presence of dead marine animals scattered across the exposed surface provides one of the clearest indicators supporting this conclusion. Fish, crabs, clams, and stingrays cannot survive prolonged exposure after being lifted above normal tidal levels. Their distribution across the newly emerged terrain strongly suggests that the coastline itself changed elevation rather than the sea merely retreating temporarily. Marine ecosystems are particularly sensitive to abrupt geological change. Organisms adapted to permanent underwater conditions become vulnerable almost immediately once exposed to direct sunlight and air. Sessile organisms attached to rocks or sediments cannot relocate with changing water levels, while mobile species may become trapped in isolated pools left behind by rapid uplift. These biological observations therefore complement geological evidence by demonstrating that environmental conditions shifted over an extremely short period, consistent with earthquake-related deformation, rather than slow coastal evolution. Fresh fractures observed near the uplifted coastline provide another important clue regarding the sequence of events. Earthquake shaking generates stress throughout both consolidated rock and unconsolidated sediments. Where these stresses exceed the material's strength, cracks develop as the ground adjusts to newly imposed forces. The orientation, length, and distribution of these fractures often help geologists reconstruct the direction and style of deformation that occurred during an earthquake. Combined with evidence of uplift and localized landslides, they suggest that the coastal landscape underwent significant mechanical reorganization during or immediately after the seismic doublet. Nearby reports of bubbling pools further indicate that underground fluids responded to changing pressure conditions. As fractures opened and sediments shifted, groundwater, natural gas, or other subsurface fluids gained new pathways toward the surface. Similar phenomena have been documented following major earthquakes in many tectonically active regions around the world, where changes in underground permeability alter the movement of fluids through fractured rock and sediment. The appearance of natural oil seepage along portions of the affected coastline adds another important dimension to the sequence of events. Southwestern Trinidad occupies one of the most petroleum-rich regions in the Caribbean, where hydrocarbons generated over millions of years remain trapped within sedimentary formations beneath both land and sea. Under ordinary conditions, these fluids are confined by layers of relatively impermeable rock and sediment. Major earthquakes, however, can alter subsurface pressure relationships almost instantly. Newly opened fractures, reactivated faults, and shifting sediment layers may provide temporary migration pathways that allow oil or gas to reach the surface in locations where little or no seepage had previously been observed. Reports of fresh oil seepage following the seismic doublet therefore fit the broader pattern of widespread geological adjustment, rather than representing an isolated occurrence. Although the exposed shoreline has naturally become the most visible consequence of the earthquakes, the processes responsible extend far below the surface. The Caribbean plate and the South American plate have interacted for tens of millions of years through a combination of horizontal motion, localized compression, extension, and strike-slip faulting. Unlike classic subduction zones where one plate consistently dives beneath another along a clearly defined trench, the tectonic environment surrounding Trinidad is far more intricate. Numerous active faults share the accumulated strain, while thick sedimentary basins respond to changing stresses in ways that differ from rigid crystalline bedrock. Each significant earthquake slightly redistributes stress throughout this network. Some faults experience a reduction in accumulated strain after slipping, while neighboring structures may receive additional stress that gradually increases their own likelihood of movement. This continual transfer of stress explains why large earthquakes are often followed by extensive aftershock sequences, as the crust slowly adjusts toward a new mechanical balance. The observed uplift near Galfa Point illustrates that earthquake hazards extend well beyond shaking alone. Public attention often focuses on collapsed buildings or damaged roads, because such effects are immediately visible. Yet vertical deformation of the land surface can permanently alter coastlines, drainage systems, wetlands, navigation channels, and ecosystems. A shoreline lifted several feet above its previous position no longer experiences tides in the same way. Areas that once supported marine life may rapidly dry, while new erosion patterns begin to develop as waves encounter an altered coastal profile. Even relatively localized uplift can influence surrounding environments in subtle ways. Tidal pools become isolated. Previously submerged rock platforms become exposed to weathering. Saltwater wetlands may gradually transition toward different ecological conditions if regular tidal flooding no longer reaches them. Over time, vegetation adapted to marine influence may decline while terrestrial species slowly colonize the newly elevated ground. Such changes unfold over months and years rather than days, but they begin almost immediately after the land itself changes elevation. The stranded marine organisms observed shortly after the earthquakes represent only the earliest and most visible stage of a much longer environmental adjustment. Another aspect requiring careful examination involves coastal stability after the initial uplift. Sediments displaced during a major seismic event do not necessarily become permanently stable the moment the shaking stops. Fresh scarps, newly formed fractures, and partially mobilized sediment masses may continue settling under gravity as underground water pressures gradually return to equilibrium. Minor landslides reported in the affected area are consistent with this continuing adjustment. Heavy rainfall, aftershocks, or ongoing groundwater movement could potentially trigger further localized slope failures, where earthquake shaking has already weakened the terrain. For that reason, geological surveys conducted after large earthquakes often continue well beyond the immediate emergency period. Initial observations document the most obvious changes, while repeated inspections identify slower deformation that may develop over subsequent weeks. Earthquakes in Venezuela are capable of becoming especially deadly because the country occupies one of the most geologically active and structurally complex regions in the Western Hemisphere. Unlike areas where seismic activity is concentrated along a single fault or a straightforward plate boundary, northern Venezuela sits within a broad zone where the Caribbean plate and the South American plate continuously interact. Their movement has created an intricate network of active faults stretching from offshore areas into densely populated cities, coastal communities, mountain ranges, and sediment-filled basins. The result is a landscape where powerful earthquakes can originate close to the surface and close to population centers, increasing the likelihood of severe damage. The Caribbean plate is slowly moving eastward relative to the South American plate at a rate of roughly 3/4 of an inch to about 1 inch per year, approximately 2 to 3 centimeters annually. Although that movement appears insignificant over a single year, the stress accumulates steadily over decades and centuries. Rocks along active faults do not slide smoothly. Instead, friction locks sections of the crust together while tectonic forces continue pushing from opposite directions. Eventually, the accumulated stress exceeds the strength of the rocks, causing the fault to rupture suddenly. The stored energy is released as seismic waves that radiate outward in every direction. Several major fault systems cross northern Venezuela, including the El Pilar Fault, the San Sebastian Fault, and the Boconó Fault. These faults accommodate much of the motion between the Caribbean and South American plates. Because many of them are strike-slip faults, similar in movement to California's San Andreas Fault, they are capable of generating powerful earthquakes that occur at relatively shallow depths. Shallow earthquakes are generally more destructive than deep earthquakes because seismic waves have less distance to travel before reaching the surface, allowing much of their energy to remain concentrated when they arrive. Geography further amplifies the hazard. Much of Venezuela's population is concentrated along the northern coastal region, exactly where many of the country's active faults are located. Major cities, transportation corridors, industrial facilities, ports, and energy infrastructure have developed within the same tectonically active zone because it has historically provided favorable access to trade and natural resources. This proximity means that even moderate earthquakes can produce significant impacts, while larger earthquakes have the potential to affect hundreds of thousands of people simultaneously. The geology beneath many Venezuelan cities also contributes to stronger shaking. Thick deposits of unconsolidated sediments fill numerous coastal valleys and sedimentary basins. Unlike solid bedrock, these loose sediments can amplify seismic waves as they pass through them. The effect is similar to shaking a bowl filled with soft gelatin rather than solid concrete. Ground motion often becomes stronger, lasts longer, and causes greater structural damage where buildings are constructed on soft sediments instead of competent rock. In some locations, saturated sandy soils introduce another serious hazard known as liquefaction. During intense earthquake shaking, water pressure within the sediment increases until soil particles temporarily lose contact with one another. The ground begins behaving more like a liquid than a solid. Buildings may tilt, roads can buckle, pipelines may rupture, and underground structures can rise unexpectedly toward the surface. Even structures that remain standing after the initial shaking can suffer severe foundation damage because the ground beneath them has lost its ability to support weight. Northern Venezuela's mountainous terrain creates additional dangers immediately after major earthquakes. The Andes extend into western Venezuela, while the coastal cordillera parallels much of the Caribbean shoreline. Steep slopes composed of fractured rock become unstable during intense shaking, increasing the risk of landslides and rockfalls. These slope failures can bury roads, isolate communities, damage infrastructure, and complicate emergency response efforts long after the earthquake itself has ended. The offshore setting of many Venezuelan earthquakes introduces another layer of risk. Much of the active plate boundary lies beneath the Caribbean Sea and the Gulf of Paria. Large offshore earthquakes may trigger submarine landslides or produce vertical movement of the seafloor. Either process can generate tsunami waves capable of affecting nearby coastlines with little warning, particularly where communities lie close to the earthquake source. Even when tsunamis remain relatively small, strong coastal currents and rapid changes in water level can still create hazardous conditions. The wider Caribbean region shares many of these geological characteristics. Rather than being surrounded by a single continuous subduction zone, the Caribbean plate interacts with several neighboring plates, including the North American plate, the South American plate, the Cocos plate, and the Nazca plate. Different sections of the plate boundary involve strike-slip faulting, compression, extension, and subduction. This variety of tectonic environments makes the Caribbean one of the world's most diverse seismic regions. As stress is redistributed after a major earthquake, neighboring faults may experience increased loading, producing aftershocks or, in some cases, additional large earthquakes. The recent seismic doublet inland Venezuela demonstrated this complexity. Instead of one isolated rupture, the crust adjusted through multiple large events, illustrating that tectonic stress can be released across interconnected fault systems rather than a single fault alone. Another reason earthquakes in Venezuela can become particularly dangerous is that thick accumulations of marine and river sediments border much of the country's northeastern coastline. These sediments are susceptible to earthquake-induced deformation such as lateral spreading, submarine slumping, and localized uplift. The reported coastal uplift near Galfa Point in neighboring Trinidad, following the recent Venezuela seismic doublet, illustrates how geological effects can extend across national boundaries. Powerful earthquakes do not simply shake the ground. They can permanently reshape coastlines, alter drainage systems, expose previously submerged seabeds, and destabilize slopes composed of water-saturated sediments.